This is Akash from Computer Science.
Nice to meet you.
And they have been requesting me to give some lectures on your works on Ramanujan graph.
All right. You should?
No,
I met you during
agreed.
Avi's 60th birthday.
What?
So, I met you during Avi's 60th birthday.
Yeah. Yeah, when he was knighted. Remember that fellow, forget his name. He was knighted, that one guy knighted him.
Silvio Macaulay knighted.
Silvio, yeah. That was quite a...
It was quite a scene.
Yes, Ramanujan graphs are very popular in
Computer science.
Computer
Yeah,
science.
that's why I'm talking about it tomorrow.
Yes, yeah. That you began very early on.
Yeah, we didn't realize it.
That it was going to become so big.
Yeah, absolutely not. No.
नहीं दरकार है
इंट्रोड्यूस करेंगे
हाँ दरकार है
हाँ लाइव हो रहा है ना
हाँ
तो
लाइव हो रहा है और उनका माइक अलग है T is arranged, no? T will be there. Yeah. Maybe you need to give a count or something, or is this a live channel or it's a Zoom? Live on YouTube. For YouTube, one usually needs a permission from the speaker.
Yeah, it's okay.
You have given? You
No,
give.
I give.
I think in most places one needs to make a real signature.
Yeah. Yeah. But YouTube, I can.
Sorry?
Will there be a recorded version of this? Could that be more channels since streaming it live?
But YouTube, once it is on YouTube, it is always there.
It'll always be there. Do you know what channel they're streaming it live?
Okay, that we have to find out.
Right.
Yeah.
We can take our time.
Yeah, no, I am myself not so clear.
Sorry.
Is it okay to read? It's perhaps not the brightest. It's not the brightest.
Yeah.
It's okay. Yeah.
How long is it? 1 hour?
1 hour. 1 hour.
the subway.
No, I think there are more places. People will keep coming for some more time. But maybe it's soon time to begin. Sorry? It's time. Okay, all right. So welcome you all to this special department colloquium by Professor Peter Sarnak. The department is very happy to welcome him to IIT. He has been to India several times, but this is his first visit to IIT. Unfortunately, he is not all that well today. He has some small cough and cold. I hope quite small, but otherwise he is always very energetic and enthusiastic, and I would have taken him around in IIT, and he was indeed hoping to look around, but that has not been possible. So this is department colloquium, and tomorrow he will give a what is called institute colloquium, which is more public lecture when I am supposed to introduce the speaker. So I have saved myself and you repetition. So I still want to say a few words. Take your time, take my time. So just to say a few words, Peter Sarnak is among the most influential mathematicians of our time, known for his diverse contribution to several parts of number theory, Lie theory, and ergodic theory. He has an abiding interest in the Ramanujan conjecture and the associated Selberg conjecture, for which some of the best results are due to him. One can speak about many honors and many things with which he is involved with, but I have just chosen to say that he already had 57 students. I mean, that's an amazing number. 57 PhD students, and he has 75 collaborators on the MathSciNet. And I should also add that the two sets are mostly disjoint. So I guess he had chosen not to lend his name to all the students who have been writing brilliant theses. The list of his students is stellar, many of whom are already world leaders and are well recognized, including our own Kannan Soundarajan and Akshay Venkatesh, who were his students. And okay, these two, since they are Indians, and that will be more related by the audience here, I mentioned, but there were many others who are also Indians in whom he has played a large role. Let me end by mentioning that most of us know the importance of a family. And Peter Sarnak thinks about the importance of a family in mathematics.
Thank you very much.
Good. I request Peter Sarnak to give his lecture, and
Okay.
yes.
I accept.
Okay, good.
Thank you very much for your very kind introduction, and it's nice to be back here, even if I am a bit ill, but I'll do my best, and if I start going into some kind of cough, you'll just understand that I shouldn't get excited, otherwise I'll start coughing. So I might talk a little low. All right, so what I want to talk about here are these base note of spectra of locally uniform geometries. I've given this lecture in a few places, and they are usually 3 lectures, so I'm taking parts of it to make it into one. So I'm going to tell a story mainly. The story where you'll see that a whole set of problems, they're all about computing something called what I'll call the base note spectrum. And I'm going to go in the first half into quite a bit of detail because there's some homogeneous dynamics there, and this is one of the world centers in homogeneous dynamics, and the work emanating from here plays an important role in understanding some of that. All right, now this might look pretty bad, so I'm going to be concentrating on some very explicit examples of this, but the general setting, I want to explain what I mean by locally uniform geometry. So globally, you might have a what's called the Riemannian symmetric space. This is a space where if you invert geodesics about each point, that's a global isometry. And Cartan classified those, and they're very close to Lie groups. And there's an analog, a p-adic analog called Brouhard-Titz building. So quotients of those spaces are what we want to study here, but we'll be studying very concrete things like graphs, hyperbolic space, and Euclidean space. Those are the three cases I want to discuss. So I would assume that we have a differential operator, or maybe a difference operator if we're in the discrete world. But let's start, I like differential operators. So suppose we have a differential operator which commutes with the symmetries of the space. The space must be, the global space looks at every point like any other point. That's very important. I don't want flabby geometries because we're going to make a big deal out of specific numbers. All right, so suppose I have a differential operator. It often will be the Laplacian. I'll define it in a second. And suppose I have a family of compact, locally symmetric spaces. I might allow finite volume, but you should think compact quotients. That's what a locally uniform geometry is. We'll see examples, as I said, in a second. And what I mean by the bass note, so the bass note is like in music, the lowest tone. Bass tone, that's where that's coming from. It's the smallest non-zero eigenvalue, if there is a zero eigenvalue. It's the smallest non-zero eigenvalue of this differential operator, which is well defined because the spectrum will be discrete. It will be an infinite set of numbers. And the smallest one in absolute value will be called the bass note. That's going to be defined in a second. And we're going to vary over these geometries and ask what values can you prescribe for the bass note. This is a practical problem, actually. In many situations, you want to engineer something which has a bass note, a spectral gap, or a Ramanujan graph, something like that. And this all fits into that picture. Now, I started out here just to make everybody scared. Fancy symmetric space. In the end, I will be telling you that it's completely boring if there's something called rigidity, that's well known to experts here. It's going to say that there's nothing interesting you can do there except number theory in connection with this problem. So the interest here is going to be very concrete, low-dimensional examples. All right. So I'm going to define this base node. So x, we've got this differential operator, the smallest non-zero eigenvalue is this. I don't say that this differential operator might, you will see examples in a minute. You think of the Laplacian. Anyway, because I'm going to allow f, the set of local geometries that we want to look at, it may be all of them possible, maybe a continuum, but also may be a discrete set. So if it's a countable set, then to actually write down each of these numbers doesn't make sense. I mean, you're not going to get a nice answer. So the base node spectrum, by definition, is the closure of the set of real numbers. So we'll have limit points, and we'll have discrete points. So it's just a subset of the real line. These are, in absolute value, the eigenvalues. And I'm immediately going to make, you're going to see all the examples of this. I'll say that the base node spectra of a family F of the differential operator P is rigid if there's only one limit point. So if there's only one limit point, it means that as we make these geometries bigger and bigger, because that's how we're going to make infinitely many of them, they can only go to one point, and so the only thing you can prescribe is that point. So I'm very interested in when rigidity sets in as we put constraints on the family F. Okay, so I'm going to talk about the Euclidean case first, but just to show you what comes in the second half of the talk, I'll talk about hyperbolic space, I'll review that, and I'll talk about three regular graphs, the simplest, interesting case of a tree and a quotient of a tree, which is the case of a Brouhard-Titz building. And the reason I want to spend a lot of time, at least half the lecture, on the Euclidean case is the Euclidean case is really interesting. And the way I came across this, I was preparing some lectures, Chern lectures at Berkeley, and I didn't know whether to talk about Markov spectrum and Markov's Diophantine equation that I've been working on for 15 years, or to talk about some recent advances, which I'm going to show you by young people, on spectra and the possible base node spectra coming from physics. And so I didn't know which to choose, and then I realized they had the same problem. That's what I'm going to explain to you. So they're actually the same problem. All right, so let's start with Euclidean space. Euclidean space is Rn, that's a globally symmetric space. And the local geometries are you take a lattice. So a lattice is a n-dimensional, n linearly independent vectors. And you take a lattice which is discrete. We want locally uniform. We take the quotient of that, and that'll be a flat torus geometrically. Now we can realize the space of these objects over which we're going to study the base note as a set of lattices. And concretely, we take the standard lattice, which is Zn, and then we take a linear transformation G in SLNR. I want to keep the determinant to be 1, so that the volume, I'm going to scale the volume to be 1. Then this homogeneous space here, SLNR of SLNZ, is the place in which homogeneous dynamics takes place. That's where it takes place. The parameter space is set up that way. But now I'm going to do something a little unusual. I take a linear differential operator, which commutes with the action, which commutes with translation. So I take any polynomial in d by dx1 up to d by dxn of some degree. I'll make it homogeneous of degree d. I take a homogeneous polynomial in these differential operators. I'm going to ask about the base note spectrum of P as I vary over all the local geometries. That's the question. Now, you usually can't compute the spectrum of a locally homogeneous space. So when we get to the upper half plane, the quotient there, this is the theory of automorphic forms. It's juicy, it's interesting, but there's nothing explicit there. Here you can write down the eigenvalues on a flat torus because the exponentials are eigenfunctions, any differential operator on e to the 2 pi I m x, this is m in the product x, will pull out the value pm in absolute value, maybe some normalization. And so the base note of the lattice for P is going to be the small, so of course, the zero mode, this homogeneous polynomial of degree 1 or higher, so it'll annihilate the constant functions. And so the smallest, so we remove 0, which is the constant function, from this e to the 2 pi mx. And we look at the set of values mod pm as m goes through the dual lattice. And so the base note spectrum is this question about what is the smallest value assumed by this polynomial. And this is a very hard problem, actually, because it depends if the polynomial is positive. We're going to try study this. And it turns out that Mahler studied this. He's got a wonderful paper in which he introduced star bodies that I want to explain, and in which he already saw that there's dynamics in this problem. Since I'm a number theorist, I'm going to also restrict, so if I have my polynomial and we allow any real coefficients, and then we move by SLNR, so we move over all SLNR lattices, all the possible lattices. I told you I want to allow myself to restrict to some lattices which are more number theoretic. So a lattice will be called P rational if, when I evaluate P at Gx, that's how I get the lattice, this polynomial of x is up to a scalar got rational numbers for its coefficients, or up to a scalar has got integer numbers for its coefficients. So when I'm in the world of rational integral polynomials homogeneous of degree d in n variables and ask which numbers are represented, well, this is the main problem in Diophantine equations. This is a very hard problem, and we're asking which is the smallest number that can, what's the biggest gap at the bottom if you want to make a rational spectrum. And so let's see what it looks like. All right, so I hope everybody, so that, I'm sorry. This rational, the rational is a countable subset of all the lattices. And so this is, I will often take that as my subset F. I allowed F, you will see I'm always going to allow F to restrict it, as I said, so as to rigidify at some point. I'm very interested when it rigidifies. All right. So as I was just saying, that when you look at the rational, it's much more arithmetic. Now, Mahler introduces a star body. You look at the set of, let's say the polynomial is real, so, and you look at the absolute value less than or equal to 1. Now, if the polynomial is a sum of squares, then this is a sphere, nice and convex. But if the polynomial is x1 times x2 up to xn, then it's got these cusps. And the geometry of numbers becomes extremely tricky because convexity is something everybody understands after Minkowski. When you're non-convex, it's very subtle. So if P changes sign and you've got these cusps going to infinity, the problem is going to be much, much harder as to what the base node spectrum is as a very overall local geometry. Now there's something called Mahler compactness. This is the paper in which he proved it. He wanted to understand what this base node spectrum is as you go over all so you fix your polynomial, you go over all lattices, and you want to know what numbers do you assume. And maybe you don't even take closure. Maybe you assume all numbers even. So he didn't take closure, but because I'm going to always allow myself to take countable subsets, I have to take closure. All right, so he proves this function is semi-continuous. And most importantly, this Mahler compactness says as you go to the boundary of the space of lattices, the shortest vector goes to 0. That's Mahler's criterion. And because of that, this value will have to go to 0. So if you're trying to see what values you can assume, it's not going to happen at infinity. It's going to happen somewhere in the middle. And then he proves it's semi-continuous. This function needn't be continuous. It can jump if it changes sign, because the minimum is not necessarily achieved in where you think it is. You may have to go far out in the star body to see where the minimum is achieved. And what's this got to do with homogeneous dynamics? He points this out. He talks about an automorphic star body. If I have a subgroup H which stabilizes the body, so suppose I have a subgroup of linear transformations which stabilize the body, then mu p over here of hg gamma, remember these are cosets, is the same as mu p of g gamma. So if you have an orbit, so if H is non-compact, and you look at this orbit, mu is constant on this. Maybe this runs out to infinity, in which case you'll be able to understand what's going on. And he uses that, but he doesn't know much about dynamics. But this is where he proves the Mahler compactness about the boundary. And of course, you can also tell how far you go out in terms of what this base node eigenvalue is by how far this goes before it maybe comes back. So this connection with unipotent flows, where H is generated by unipotent orbits, was a tremendous insight by this fellow sitting right in front here, Raghunathan, and completely led to the solution of one of the problems I'm going to tell you about, which is the Oppenheim conjecture, because Raghunathan made conjectures which were proved by Margulis, the weakest Dani pursued it further, importantly, and the most important complete theory is due to Marina Ratner, measure rigidity, which was Raghunathan's conjecture. And what that theory is that if the H has got unipotent elements, then what happens to the orbits? Every orbit, not almost every orbit. Let me make something clear here. We're not doing statistics here. We're looking at every possible value. And we're particularly interested in some values which might be a rational thing. So we're not saying almost all, though knowing what happens at almost all is extremely useful. So this measure rigidity is about every orbit, the classification of every orbit. All right. So let's see some examples, because what this lecture is I'm going to show you a zoo of base node spectra. Some are juicy, some are boring, some are really, really juicy, as you'll see, and some are extremely important. So here's one that's very important but boring from our point of view. Suppose I take x1 squared plus xn squared, the Laplacian, and then I look at this polynomial on the space of lattices, and I look at the smallest non-zero value assumed. That's a continuous function. So if the star body is bounded, Mahler shows the function's continuous, and in that situation, the spectrum, the base node spectrum, will always be an interval. So it's I'm interested in what the structure of it is, but of course I also want to know what it is. So the mankind is worried about what this is in this case. It's called Hermite's constant. People still work on trying to understand this. The only issue is what's the top value? It's an interval starting at 0. What's its endpoint? What's a lattice with the longest, shortest vector? That's what the endpoint is. And this is known in dimension 2, 3, up to 8. The E8 lattice and the Leach lattice in dimension 24 do the job, and in dimension 24, it certainly follows from recent work of Vyazovska, but I will return to something called the conformal bootstrap, entering into this a bit later. This can be proved more elementarily, so not the sphere packing, but just the lattice packing. Kohn and Kumar did this for those cases, and in no other dimension do we know the value. So the interesting problem here is a very engineering problem. What is the endpoint and how does it behave when n gets large? Certainly interesting, but from my point of view, structurally, is it rigid? Is it an interval? Is it got a fractal nature? That is not, here it's an interval. Yes, very good. Minkowski computed the average. Okay, come to me after the lecture. I don't want to take my time. I have to talk slowly, and I have a very good answer for you, because people don't understand why Minkowski proved the average by never saying he's taking the average. He uses something called his mass formula, which secretly is doing something. And so the answer is the average is very near the maximum when n goes to infinity, which is why the problem is very hard to understand. So if the average already gives you something, and it's almost impossible. The improvements of that are absolutely tiny. It's a bit like these combinatorics problem in it's where you.
This is not the definition of the Hermite constant. It has a definition.
It's equivalent. Hermite constant is some. It's exactly the same. It's some change. Hermite constant.
It's not something explicit.
No, it is. In every dimension, it's just we don't know what Hermite constant is in any dimension except that.
No, it's not some pi to the power.
Oh, yeah, no, it's got a, no, yeah, there's some factor there, of course. There are factors there, but my whole view here is if I'm starting with lattices in Rn, I'm doing this up to scale. So in Euclidean space, you scale to volume 1, or you don't scale, you make another normalization. You are correct, but it doesn't change. If you know the one, you know the other. All right, now, since we know x1 squared plus x2 squared, I'm now looking at two variables. Okay, one variable is trivial. The spectrum, if I have at least two variables, and I have a1 x1 plus a2 x2, and I vary over x1 x2 integers, a1, a2 are two or more variables, I can always, by Dirichlet's theorem, make that arbitrarily small. So the spectrum, the base node spectrum of a linear differential operator on the lattices is trivial. It's just zero. There's no gap you can make. It's completely uninteresting. Let's take a quadratic in two variables. So the one quadratic in two variables was x1 squared plus x2 squared, and we know the answer. It's the hexagonal lattice. There's only two quadratic forms over the reals. You're allowed to make real changes of variable. It's a law of inertia. So the signature is either 2, 0 or 1, 1. And if it's 1, 1, the quadratic form is xy. So what's the base node spectrum of xy? That's a nice star body. Fantastic answer. So this is an automorphic star body. There is an action. So if you take x1, x2, you can multiply x1 by lambda and x2 by 1 over lambda, and that preserves x1 times x2. So there's a diagonal action, and diagonal actions are not rigid until we rigidify them with commuting families. So this is going to be complicated. Everybody knows that, because this is going to be like the geodesic flow on SL2R over SL2Z. But it was computed by Markov. I told you that. And this is the most spectacular spectrum that Mahler and Davenport and all those fellows were trying to generalize. They were so taken by this spectrum. So the base node spectrum of the wave equation, which is d1 times d2 in two variables, I mean, nobody computes it, but it's not hard, is this set. It's got an infinite discrete set of numbers above 1/3 that Markov brilliantly showed correspond in a one-to-one correspondence with solutions to a cubic Diophantine equation. And let me assure you, cubic Diophantine equations in affine space are completely mysterious. Mankind doesn't know which numbers are sum of three cubes. You can say what you like, nobody can prove or disprove you. So nobody knows which numbers are sum of three cubes. They are log K3. That Diophantine geometry is very hard, but this Markov equation is understood much better. And he shows the solution to that equation parameterize the discrete spectrum above 1/3. And at the bottom, there's a whole array from 0 to mu naught. There's an exact number that Feynman computed. Paul computed array. Feynman got the exact endpoint. And in between, it's fractal line. That is about as juicy as any base node spectrum is going to be. So I told you it's going to have a discrete part, continuous part, and maybe a fractal part. And that has got it all there. And are there other cases where we have this? That's the interesting question. All right, now let me take the rational. What is the base node spectrum of those quadratic forms which up to a multiple are rational? It turns out that's obviously a subset, and it's called the Lagrange spectrum, something a little different. The Lagrange spectrum is usually defined through Diophantine approximation rather than a base node. That is, for every real number alpha, you look at the lim inf q goes to infinity of the distance from alpha q to the integers times q. And that's a very weird function of alpha. And you ask, what values does it assume as you go over all alpha? Turns out the Markov's already closed. You don't have to close it up. It's already closed. And this is Lagrange is also closed. So this Lagrange spectrum is a subset of the Markov spectrum that, because we just, now this was proved by Kusick. That's not obvious, but you can give a dynamics proof, because what you can do is you can show that if you have, you can reinterpret it in terms of how a geodesic in the modular surface, whether it runs off into the cusp or not. And if it doesn't want to run off into the cusp, you can always find a periodic, it's called the Nosov closing lemma. You can always find a periodic orbit which mimics that guy for as long as you want. That means you can find periodic, and the periodic orbits are the rational guys, and that gives another proof of this fact. That it's contained. That it's not equal is much harder. I think Feynman was the first to produce a point. And just last week, 2 weeks ago, a paper was posted by these Brazilian fellows who've been working on this Markov spectrum. And they show that to the left of 1/3, remember the spectrum, above 1/3, the Lagrange and Markov are the same. And in the bottom ray, they are the same. But in the middle, there's points in the Markov which are not in Lagrange. And this theorem here says that those points can be found in any little neighborhood, arbitrarily small neighborhood of 1/3 on the left. These are hard things. All right. So that's a story in 2 variables for degree 2 and 1. Now let's keep with 2 variables and look at higher degree. So what about d greater than or equal to 3? So Mordell and Davenport worked on this, but they weren't able to prove what George, so I have a student finishing, he's not Indian, he's Greek, Kotsovolos, he's finished a beautiful thesis. When you take a polynomial of degree 3, homogeneous polynomial of degree 3, like x cubed plus y cubed, that would be an example. Under the reals, you see whether that polynomial, after you dehomogenize, has how many real roots it has. That will be the real orbit of SL2R will maintain that. There's some invariant theory. If you look at that polynomial and you ask what its maximum is, so Davenport, actually Mordell first found the maximum. So they are these numbers that you see over there. And Davenport showed that the top is not isolated. So he was trying to see if you have a Markov situation there. But let me firstly emphasize that x cubed plus y cubed that stabilizes compact. Ergodic theory does not, on the face of it, bias anything. Though George has done something where you get the ergodic theory from somewhere else, but not directly from that. So it's clear that just ergodic theory is you have to have a non-compact orbit in order to have some interesting closure properties. And that immediately makes these very different. And what George does, by direct bare hands, continued fractions, and some very nice hard analysis, he shows that the base node spectrum is always an interval. He doesn't know what the top is, but for every degree d greater than or equal to 3, the base node spectrum of a polynomial of degree d in 2 variables is always an interval. Now, I mentioned, yeah, I'm going way too slow, but I'm going to just finish in an hour. That's all. Oh, no, I'm doing well. Nearly halfway. That's okay. So there's one case where we do know this. I was in a lecture that you were, Selberg's 70th birthday, in which Margulis announced the solution of this problem. And Castles and Swinner, the guy who'd worked on this problem for many, many years, I was sitting quite close to them. And then so the name of Margulis's talk was Some Applications of Ergodic Theory. He wasn't sure it was so interesting. You told him it was, so he was giving a lecture. And then Castle said, "Is that our Oppenheim conjecture?" And Swinner and I said, "Yeah." So Castle pulls out all the snuff, wants to stay awake in the lecture. And he stays awake, and he's just marveling for a while. But then I looked about half an hour later, he was sleeping again. But they gave seminars on this immediately afterwards. It was a big, big thing. This comes from homogeneous dynamics. So this is a star body. If we have a quadratic form, so we're now looking at all differential operators which are quadratic. Most people will tell you that the only differential operators are second order. Okay, so the quadratic ones are certainly interesting. So over the reals, we have a polynomial, quadratic, so the signature is the important thing. And if the signature is positive definite, then we already know the spectrum is an interval. If the quadratic form is signature n1 at least, so there's at least some not positive definite, then it changes sign, and then the answer is going to be very different if I have 3 or more variables. And that's because the stabilizer of the star body, H, is an SO21, which is generated by unipotence. And so the whole of Raghunathan's machinery comes in, and Margulis was able to do just enough to prove this non-escape of mass. Not the whole story. And then the spectrum is fantastic. So the spectrum in 3 variables, positive definite we know is an interval. Indefinite is rigid. It rigidifies. There's a guy at the top that Davenport certainly knows. These come from number fields, periodic orbits of some H action, and they accumulate at 0. You can't make any gap. The base node spectrum is rigid. So this is exactly what is being proved there. And if you have a signature in 4 variables, you can have signature 2, 2, 3, 1. It's same. We know what they are. And if we have 5 or more variables, see, these guys, these discrete guys, unlike the case of Markov, they're much simpler. They are coming from isotropic rational quadratic forms that represent 0 non-trivially. There's a solution to f of x equals 0 where x is not 0. That's where, sorry, anisotropic. My apologies. They're coming exactly from the anisotropic ones which do not represent 0. And if you have 5 or more variables and you're indefinite, and if you're indefinite at infinity, usually it's an old guy who doesn't know how to switch off his, that's me. I'm glad to see it's a young Indian guy. Okay, it's not fair. So these points in the spectrum are anisotropic rational quadratic forms, and there are no indefinite rational quadratic forms in 5 or more variables. That's the Hasselmann-Minkowski theorem. There's no local obstruction. So the base node spectrum, if you have 5 or more variables for a quadratic polynomial, is exactly 0. All right. The holy grail in the subject is the case that Castle, Swinner, and Dyer understood very well in terms of dynamics, and that is the base node of x1, x2, x3 over all f3. Now, the reason something changes here is that the stabilizer of the star body is lambda 1, as you can see, lambda 1, lambda 2, 1 over lambda 1 over lambda 2. That's now a diagonal action, but it's commuting diagonal action. And it was a fantastic insight of Furstenberg many, many years ago to understand that this allows you to rigidify. Like in Ratner's work, it's just we don't know how to prove it in this case. So the theorems that are proved in this are very substantial by Einsiedler, Katok, and Lindenstrauss mainly. But those theorems require that some limit measure, some weak star limit measure that you make has positive entropy, and that's not something that you can put into the question. So these problems remain unsolved, but the rigidity is expected to be true. And that would mean that this is rigid. And Castles and Swinner and Dyer do numerics. By the way, Swinnerton and Dyer was a good, you know, there's something called the Birch-Swinnerton and Dyer conjecture. He was a whiz at doing numerics. So he computes many of these numbers in the top of the spectrum here, and they have an isolation theorem, so they conjecture the spectrum is rigid in another language. So this is a holy grail. What we don't know is measure rigidity for diagonal actions unconditionally. And again, Davenport, so the only other thing in 3 variables, that's 3 variables, so there's this that nothing is known about, and I have some speculation, so I don't want to waste time on that. But Davenport and Rogers proved that if you take not the product of 3 linear forms that factor, but a product of x1 times x2 squared plus x3 squared, that's a good polynomial. That's got a rank 1 action, so you don't have measure rigidity playing the game. And in that case, they show that the top, you see, they're looking for Markov. They're looking for Markov, but they show that the top is not isolated. So there's not isolated, so it doesn't look like Markov. But what Kotsavalos does is look at the rational base note spectrum. This is a base note of this base. On rational, sorry, he's looking at it there, and he shows that the top is isolated and that there are infinitely many limit points. So this is a good candidate for there being a Markov-like spectrum for this polynomial in 3 variables. And now, just because I want young guys to work on this, and I've come here all the way because that's why I'm spending so much time on this Rn. This is what we know about this problem. So this is polynomials of degree n in d variables. So Margulis proved this. If we are quadratic polynomials and n is greater than or equal to 3, then we're rigid. And Kotsavalos is if we are in 2 variables and d is greater than or equal to 3, then we are an interval. And down the diagonal, here's what I was just looking at. Very subtle, because the degree and the number of variables are the same. That's always the toughest. And the question is, I would imagine the top half is more or less intervals, and the bottom half should become rigid. But I don't know, and we know nothing. So this is all we know of these 2 extreme lines, Margulis and Kotsavalos. Okay, so now how much time do I have? I wanted to spend some time on that. Okay, so I've spent 40 minutes on that, so I have to be quite fast here. So I'm going to now describe 2, I won't go into a hyperbolic 3 space, I'll go to hyperbolic plane and 3 regular graphs and talk about the base note spectrum. Exact same problem, you'll see similar pictures, and they carry tremendous weight in terms of applications. So the hyperbolic plane is the upper half plane with the line element ds squared is dx squared plus dy squared over y squared, is constant curvature minus 1. The symmetry, the isometries, this is a globally symmetric space, is the action by projective linear action. Z goes to az plus b over cz plus d. This is an isometry. So there's your group. And we're looking at compact quotients. And I'm going to tell you a bit about the spectrum of the Laplacian. Now we're going to take Laplacian. If we go to a hyperbolic 3 space, we would look at Laplacian on 1 forms, cohomology, but this is richer now. And I'll skip 3 space. And the 3 regular graphs, finite 3 regular graphs, are the other ones I want to look at. And so I need to define the Laplacian on a graph. So I'll call the 3 regular graphs, that's my set of local geometries. So 3 regular graph is a finite 3 regular graph. Its universal cover is a 3 regular tree. That's a locally uniform geometry. And I want to go over all these finite guys and ask, what can I make lambda 1 be? And lambda 1 is the base eigenvalue. So the Laplacian on a graph, in general, Laplacian on f is the degree of the vertex v times f of v minus the sum of all w that join v times f of w. This is non-negative. If f is constant, I will get 0 because I've got dv there. So the 0 eigenvalue is 0, and then lambda 1, the base note, is the next biggest eigenvalue, and the graph's connected if and only if lambda 1 is bigger than 0, which I will assume the graph's connected. So we get a spectrum, and if I'm 3 regular, then it's very easy to see the spectrum is in 0, 6. 0 occurs only with lambda 1. I'm going to look at how lambda 1 goes. And if I'm in hyperbolic space, I do the same thing. I look at lambda naught, it's 0. And I should tell you what the Laplacian is. It's the divergence of gradient with respect to the metric. I didn't write it down, sorry. Now, before I tell you what the base note spectra look like, there's a fantastic answer to this. I need to tell you some, so you're not completely shocked. So with the three-regular tree, you can ask, what's the spectrum of this operator, Laplacian, on L2 of the tree? Now, I emphasize L2 of the tree, the Hilbert space of square summable functions on the tree. So the spectrum, I don't want bounded eigenfunctions. I want the functions to be close to L2. And that makes the spectrum, and this is computed by Keston and by Sally and Schleichen as a two-adic Plancherel density for PGL2 Q2. The spectrum is in this interval alpha, 6 minus alpha on the universal cover. So there's a gap to alpha. Alpha is about 1.75. And at the top, there's a gap 6 minus that. So the spectrum on the universal cover is restricted in this way. And for hyperbolic space, there's a similar thing. The spectrum on the universal cover in dimension 2 is a quarter infinity. You knew a quarter would be coming. That's a Selberg conjecture. It has to come. It's going to be, of course, the last slide. All right.
Why did you take Q2 in the previous example?
Because I'm doing 3 regular graphs. 3 regular. So I could do any D regular. I could do any D, but 3 is the first interesting and by far the most interesting case. D equals 2 is boring because it's just a cycle. No spectral gap. All right, so let me save time with drawing pictures of what they look like. Here's an amazing theorem of many, many people. So what's the base node spectrum of cubic? So it's the interval 0 alpha, the closed interval 0 alpha, and then an infinite set of points above alpha. And the fact that there's an infinite set of points there is a deep fact. These are super Ramanujan graphs because they are guys who have their lambda 1 bigger than this lower bound of alpha in the construction. So the spectrum is infinite above alpha, and it's discrete, and it's in the interval 0 alpha. So the limit points are 0 alpha, and the other part's discrete and infinite. Now, if you restrict to planar graphs, then it's a well-known theorem that a planar graph can't be an expander. So I'm not going to define an expander, but an expander is equivalent to there being a spectral gap here at the bottom. There are other definitions. That's a theorem in computer science. So if you stick to planar graphs, you can't make a gap, and you rigidify. So the base node spectrum just goes down to 0. So that's the story for the base node spectrum of 3 regular graphs, and I said it's due to many people. And there's a stop press here that I want to mention. That's really interesting. That's only 1 week old. So I'm really excited by that. So if you look at planar graphs, I just said that lambda 1 goes to 0. There's something Lipton and Tarjan prove you can always find a separating set, which makes the two set, okay, which makes lambda 1 small. What lambda 1 must go down to alpha? I said it was discrete, and the best result that's known there is that lambda 1 is less than alpha plus 100 over log of the cardinality of x. So as x goes to infinity, lambda 1 must go down to this alpha, so the spectrum is discrete above alpha. Why are there infinitely many? Well, there are Ramanujan graphs that Lubotsky, Phillips, and myself constructed, as did Margulis. But if you want to make these super Ramanujan graphs, you have to go into the proof of where that came from. And a critical thing in the proof of why these graphs are Ramanujan is the proof by André Weil of the Riemann hypothesis for abelian varieties. That's what controls where the eigenvalues are eventually. And if you want to make the eigenvalue at the top not occur so that we get some gap, then you need to know something about this eigenvalue interpretation of the zeros of the zeta function. Now, Weil gave 2 proofs of the Riemann hypothesis during the Second World War. The other proofs is an elementary proof of Stepanov. I'm talking about for curves over finite fields. But he gave 2 proofs during the war, and one was just genius. It's we take a surface theory. It's just one of the unusual for Weil. It just sucked this new. Usually it's big machinery. This was just very clever counting. But the other proof was to go to the Jacobian, use the Rosati involution, and in that proof, the action of Frobenius on cohomology is semi-simple. It's the only case we know that. So all the generalizations of proofs of Ramanujan, we don't know the semi-simplicity. This is something Grothendieck had always dreamed of, something called the standard conjecture. It's not been achieved. So That proof you can use, and was used by Coleman and Eidixhoven to show that you can actually not have the eigenvalue 2 root p in the spectrum for certain graphs for gamma naught, and using crystalline cohomology. And Zubralina used that. Now there are 2 other proofs. These computer scientists I used to give lectures and say, you guys will never make Ramanujan graphs without number theory. Well, the first blow was maybe 10 years ago when Srivastava, Spielmann, and Saxana, no, not Saxana, Marcus, Saxana's ago, proved primes in P. They constructed Ramanujan graphs using interlacing polynomials and using some theorems from statistical physics, Li-Yang theory. I'll mention it in my public lecture tomorrow. It's very interesting. And they constructed these, and it was quite an achievement. And from their proof, you can do better with these super Ramanujan graphs than ours. But the best thing here is you could ask whether a random graph is Ramanujan or super Ramanujan. So what's the probability if you take a graph on n vertices, you take a standard random model, what's the probability it's Ramanujan? And I have a bet with Nogal on that he said its probability is 1, and I said it's 0. Because I didn't want it to be true, and he wanted it to be true. And it was very clear that he's wrong, because when you started to numerically experiment, lambda 1 started to come down. But in 2002, in an REU, Steve Miller and others in an REU that I was running did some numerics and found that this lambda 1 distribution looks like Tracy-Widden. That's something in random matrix theory. And if it's that, then you get not 0, not 1, but exactly 69%, which was proved last week by Wang, McKenzie, and Yao. And this is, I've been waiting for this since 2002. The random guy is Ramanujan, and that's the best way to prove it, its existence. Yeah. D is 3 here. Yeah. Something, D is fixed. Absolutely. Now, if you allow D to grow slowly, they had proved this. Yeah. Yeah. No, that's a very good point. All right. Now, actually, I've got 13 minutes. So why not just tell you an amazing theorem? This is the base note spectrum of hyperbolic orbifolds. So I'm looking at all hyperbolic surfaces in the plane, all local geometries, which are the hyperbolic plane divided by a discrete group compact quotient. And I'm asking, what is lambda 1 of the Laplacian? And that's the answer. There is an interval, and I'll tell you what this interval is in a second. And there are 4 outliers. So there are 4 surfaces which have lambda 1 bigger than the endpoint of that interval. And then the lambda 1 takes all these values on this interval. Okay, this is a theorem that if I told you it's true, you probably start thinking how you might prove it. You've got a computer, you start running linear programs. Turns out this comes from the conformal bootstrap, something in statistical physics, in a completely natural way, and it was done by Mazak, Powell, and Kravchuk. Kravchuk, Mazak, and Powell a few years ago. In fact, Mazak comes into my office, the physicist sent him to my office, saying I might be interested in this. Boy, was I interested in it. And then I said, where does it come from? And then he starts telling me something called the conformal bootstrap. All right, I'm not going to be able to do justice to this because I want to end the lecture. Compact orbifold. It's very important to orbifold. Compact, and this should be rotated. The 4 orbifolds that appear, there are 5 over there because there's 1 on the end, are hyperbolic arithmetic triangle groups. And the Hurwitz group, which has got the smallest volume, you might think has got the largest lambda 1. And what these guys have is they've developed tools to estimate in conformal field theory. This is what this bootstrap is called, the crossing equation, a method to estimate invariants, numbers that are in scaling dimensions, of which there are infinitely many scaling dimensions, so it's like a spectrum. Nobody knows how to make the interesting conformal field theories. That's why they're stuck. So they go to the machine and they try to see, well, if there is such a theory, can I give bounds for these numbers? And this fellow comes from that school, and he's one of the experts, and he's ran this in the setting of the upper half plane, where it's much more elementary. And when he runs this crossing equation, he immediately gets bounds which depend on the, if you have gamma, so there are a few things that are important there so that you're not completely mystified. The group gamma is a discrete group, and unlike any other Lie group, gamma is not rigid in SL2R. They are deformation spaces. So that interval you see there is some specific deformation space, which is covering all the other stuff. It's all underneath there. And then the theorem says that if you aren't in that deformation space, then lambda 1 must be bigger than the endpoint of that. And that comes from a pure thought calculation involving this conformal bootstrap. And Advay, I have a student who comes to Mumbai. His grandfather lives here. So he comes quite often, and you should definitely ask him to give a talk about this, which
These are all triangle groups.
the ones, the four at the top are triangle groups. They're rigid. And one that the family that's continuous is orbifold. It's genus 0 with cone points 2, 2, 2, and 3. That's got a moduli space of 1 complex dimension. And that's where you get that interval from. And this comes really easily out of this conformal bootstrap. And they're trying to understand these conformal equations. And in general, this is very hard. But in this very baby case, Advay has given some interesting converse. And if you ask him, he'll give a lecture. This is for you. The data you give in these crossing equations are the eigenvalues of the Laplacian, the dimensions of holomorphic sections of weight k, that's Riemann-Roch, and these triple products as data. And from that data, you write down crossing equations, and they determine everything, and they determine gamma backwards. That's his remarkable theorem. All right. I should even add that this Mazak, Rastelli, and Hartmann give a new proof of Vyazovska's theorem using this conformal bootstrap. So Vyazovska's genius is that there's this infinite dimensional linear program that she solved. That's why she received the Fields Medal. She solved the sphere packing in dimension 8, and then jointly with others in dimension 24. That linear program, the Cohn-Elke's linear program, she showed, it's an infinite dimensional linear program, and she wrote down using complicated integrals with funny modular forms with different weights and ratios. She just cooked out of her thumb the extremal in this linear program, thus proving. So that in this linear program and in this bootstrap here, there's no discrete group that's input. Only the data I wrote down there. The crossing equation, there's no gamma here. Just the topological data and the triple product numbers and the spectrum. Something very interesting going on here, and we need to understand it. All right, so since I'm probably running out of time, and I do want to talk about 2 more results and then stop. So the base node spectrum of Mazak et al. Is an interval and then 4 outliers, which is a remarkable thing. But now let's restrict. I insist on restricting until I get rigidity. I want to see at what point does rigidity come in. So the reason that the spectrum was an interval and 4 guys above was because I had this moduli space that lambda was continuous on that, and it was sweeping out a whole interval secretly and then covering where all the action is. Now, if you move in our circles, then you obviously look at the subset which are arithmetic. That's a countable set, and by a theorem of Borel and another Prasad, the number of, so I'm going to tell you what the base node spectrum is on arithmetic 2 manifolds. So on all orbifolds, it was that interval and the 4 guys above. And now I told you these guys are arithmetic, so the 4 guys above are still there. But now it looks much more like the 3 regular graph. This is a conjecture. It's all but proved. There should be an infinite number of guys here above a quarter. And then this interval should be complete. You can make lambda 1 accumulate at any point there as you go over arithmetic manifolds. The set of arithmetic manifolds is countable. So you need to take closure, and now so you don't have this interval that was hiding everybody, and now you go down to this number a quarter, just like in the 3 regular. All right, so the fact that there are only finitely many arithmetic manifolds of area less than a given x, that's a theorem of Borel and Prasad. So the volume, the area must get large, and then it's very easy to use the trace formula which is something that's useful in this context, to show that lambda 1 must go down to a quarter if the volume goes to infinity. So this proves the spectrum above a quarter is discrete. But it doesn't show you anybody inside there. These, okay, and you know what we don't know, so this is why this is a hard problem. Anyway, nevertheless, for arithmetic, using some really interesting new ideas in free probability theory and some work of Hogerup and Thorbes, Jonson, and Bordenave and Collins, who did it in the graph case. So there's some notion of strong convergence rather than almost where all the most eigenvalues lie. There's an issue of where the outliers lie, the norm of operators, that's strong convergence, developed by these fellows and used by Maggie and Hyde. And they were able to show that you can find an infinite sequence of arithmetic surfaces whose genus gets larger and larger, it would have to, and whose eigenvalue gets arbitrarily close to a quarter. So we get a quarter is in the base node spectrum.
It goes to quarter, but from above.
Their proof is saying that from below. No, we don't know that there are infinitely many above. We don't know that. That's why the only reason the conjecture is not solved is that the discrete spectrum, I don't know, is infinite. So the base node spectrum on arithmetic is a quarter in, this is the conjecture, a quarter and then infinitely many above, 0 quarter, and they have proved that 0 quarter, every point in 0 quarter is a limit point of arithmetic large volume. That's using this free probability theory. Very impressive result. And at the fact that there are infinitely many above, that it's discrete from above is following, I was saying, well, that's true. But the fact that there are infinitely many above, that is unknown. All right, so now you know what my next step is going to be, and then I'll stop. And that's, of course, the real holy grail in the subject. And that is, we've now done all orbifolds, and we had the base node spectrum. Then we restricted to arithmetic, and it became quite juicy, and even we know something. And now I stick to something that's the only important ones in the theory of numbers, because they come from modular forms, automorphic forms. They're called congruent subgroups. And for the congruent subgroups, this is a very famous conjecture of Selberg that was mentioned, that lambda 1 is greater than or equal to a quarter for a congruent surface, any of these congruent surfaces. And we don't know that. The best is actually, as you said, the result of Kim and myself and Blom and Brumley. So we don't know that. And we certainly don't know that there are infinitely many above a quarter. And I can tell you how one may prove that if you assume some conjectures in Galois representation, but it's very conjectural. So this problem, the Selberg conjecture, is the holy grail. The reason I call it Ramanujan Selberg plus epsilon. Ramanujan Selberg says lambda 1's greater than or equal to a quarter. This says there are infinitely many guys above a quarter. So that's what I'm calling the epsilon. All right, I'll skip hyperbolic 3 space, which is very interesting. And let me just end with rigidity, real rigidity. So if you're in higher rank, so I was talking about hyperbolic space, a tree. I wasn't talking about a Brouillard-Titz building of higher rank, some Ramanujan complex, nothing funny like that, or even higher rank SLNR kind of things. And the reason is there's an amazing theorem that I'll state in higher rank. I'll skip this. But let me just tell you a notion and finish. This is a very important notion. Binjamini-Schramm convergence. Suppose I have a sequence of locally uniform geometries. So the global geometry is the universal cover, and the local guys look like the global guy locally. Now suppose this sequence of local geometries looks like the universal cover on bigger and bigger balls. Then whatever's in the spectrum of the universal cover, because these things are, the L2 spectrum has got to do with compact support, you can already achieve them in a finite cover if what's called the girth or the injectivity radius goes to infinity. However, that is usually, there are many examples where that's not true, but let's relax that condition. Suppose that for almost all balls in X, in the sense of measure, they are injected into the universal cover with bigger and bigger radii. So almost all just means most points in the sense of volume. Then you say this sequence converges Binyamini-Schramm to the universal cover. And if it converges Binyamini-Schramm to the universal cover, you can't make any gaps and you can't play all these games. So you get immediately rigidity, and then the whole problem is pure number theory for another reason, but that's, so here's an amazing theorem by, they call themselves the Seven Samurai. Aubert, Bergeron, Bringer, Gelander, Nikolov, Rambold, and Semet in the annals.
And Mary Aubert, no. Some other Aubert.
No, a different Aubert. Aubert. Not, now you, yeah, I misspelled it because, like you, I'm in the theory of automorphic forms, so sorry. So if you're in a higher rank, then using a lot of rigidity results of various type, any sequence, always Binyamini-Schramm converges to the universal cover. It's always true. You can't help yourself. You have to look like the universal cover. You can't make a long sausage. You can't make something funny. And that's why all the action with interesting base note spectra are hyperbolic space, graphs, and Euclidean space where there isn't this rigidity. So this is an amazing theorem which says that once you've kind of made all this, in this case, there's a generalization of Ramanujan. You have to formulate it very carefully. But if it's true, then all the spectrum is put in these tight regions, and you can't make any holes in there. You've kind of paid the price of, there's no more gaps to make. And so prescribing the spectra is no longer feasible. All right, I'll stop there. Thank you. Yeah, at 5:01, I actually. Yeah, there's a. Yeah.
You know, I thought this BSB stands for Burger Sarnak. It is not, because there were some other words.
Yeah, no.
It's not Burger Sarnak.
It's Binyamini-Schramm. It's a very important notion in probability theory. So in graph theory and in planar maps, and it's a much more elaborate notion. You don't just have to converge
but
to it.
Sarnak is also about.
You're right. It's a very simple.
L2G being approximated by.
It's got the same flame. You're right. Yeah.
About the Ramanujan
Right. But we never said for most points, which is what's universally true. So you can't help yourself but Binyamini-Schramm converge in higher rank. It's very nice. So the spectrum rigidifies. I told you I want to see it rigidify. It rigidifies from other rigidity, which is not unexpected. Yeah, you're right that the notions are not so different.
No, when I saw BS, I
Yeah.
you were being polite.
No, it's Binyamini-Schramm. Yeah. Yeah.
So in Oppenheim, this forms of Q1 and Q2 play a special role. They have different characters. Does that show up over here in this section?
Okay, so when you get to this symmetric space, which is an irreducible symmetric space, you see Rn, I'm using these other differential operator which commute with translation and not with rotation. So if you have if you took a product of hyperbolic planes and then took the Laplacian in one minus the Laplacian in the second one, you would have a theory that I'm sure is very rich and I know nothing about. And it would look like the geometry of numbers. But so far, the only thing we've looked at are the guys which are Laplacian, which are important for Ramanujan and certain applications. So these other, where that the wave equation has this Markov spectrum. I don't know that any physicist would say, I'm going to take the wave equation, computed spectrum on a flat torus. You know, you're coming back in time and you're doing something strange. But that's exactly what the Markov spectrum is. And he formulates it that way. He doesn't say it's a differential operator. He just says for any quadratic form, he talks about mu f, which is the inf. And it's clear that this is what that whole school, Davenport, I think what happened is they were doing this and then they couldn't do Oppenheim. And then Oppenheim came and then they had gone on to other things like BSD. So they didn't come back to this, and I think it's time to come back.
And what is the fractal part in
The what?
the fractal part?
So right, people are still discovering it. Like, so the fact that there's points, so there's some gaps, and there's some conjectures about the measure or the Hausdorff dimension. I don't know all that. This is the middle is a mystery to me. It's a transition from an interval. But the fact that Markov, you realize how he wrote down the eigenvalues as a solution to a cubic. It's just incredible. And there are many proofs, but he understood it completely. I think that's what they were always trying to generalize. They always talk about Markov and then, we don't see any Markov. I think Oppenheim was sort of at the center, and then it was solved by dynamics. And of course, as I said, Castles and Smith and I immediately had seminars on it. So it's not, but they were already working on other things.
Are there precise questions about higher dimensional homogeneous forms taking the integer valued points of a high dimensional homogeneous forms instead of Oppenheim, which is for quadratic form?
Right. So I was.
And
Yeah. Let me just say, the problem is incredibly hard. Take x cubed plus y cubed plus z cubed. No, plus z. Well, it doesn't matter because it's a cube.
Yes.
So take this polynomial, which doesn't factor into linear forms. So we don't have dynamics.
Okay.
And I believe that the rational spectrum of that is rigid. Let me tell you why, if you have a second. So the rational spectrum would say you're looking at rational cubic forms in 3 variables, which they're given by invariant theory, I and J. So you fix the I and J because you're looking at SL3 acting on this. So that doesn't matter. You're looking at all those, and you're asking, what's the smallest number that cannot be represented by this form? Because that's the gap, and its relation to the discriminant. So the geometry of numbers, that's what that convex region is. So the relation to the geometry of numbers is that that number is less than the discriminant to some power. And you want to find forms where they actually achieves some fraction of that. That would then make something interesting. So I believe it's rigid for the following reason. If you take, I was joking, I said, which numbers are sum of 3 cubes? So most of us believe that any number which is not 4 or 5 modulo 9, that's a local obstruction, is a sum of 3 cubes. Okay? I believe it. Then, and they vary.
Of integers.
Yeah, and you allow negative numbers.
Okay. Yes. Negative. Yes.
So what this problem is saying is taking a similar cubic form in 3 variables. So if that's true, so people look for local obstructions, and there's something called the Brouwer-Manin obstruction. In those cases, if those don't work, we tend to believe it's going to be true. If that's true for all cubic forms, which once you say for sum of 3 cubes, why not for the others? Then you would have that there's always going to be a small, you can't make Brouwer-Manin obstructions and local obstructions persist up to the discriminant to a power. So you'll always have small numbers that are represented, and that'll mean that the smallest number is rigid. So I speculate, but this is really a hard problem. So they clearly didn't even. So Mahler asked the question, but so I don't know, but I'm sticking my neck out and saying that x cubed plus y cubed plus z cubed is rigid. The rational spectrum. I don't know about the real spectrum. That's Diophantine approximation. I have less confidence.
All right. So if no more questions, let's thank the speaker.
Sorry, what?
There should be a key somewhere.
Okay. And that's going to be on YouTube. I'm not so happy. I said that Castles, remove this. Remove the Castles with his snuff, please. Should not be on YouTube.
Yeah, by now, I think if we make a mistake, it will become more famous.
Hey, good to see you. Maybe you. All right. Well, I hope I got them interested.
No, I'm sure. No.